All righty, folks, we're going to go ahead and get started. Welcome to the last colloquium of the semester. This is weird. I'm hearing myself talk in my ear. So this is the second half of our APMS 698 class. Okay, of our APMS 698 class, we have 3 more presentations in honor of our 3 dapper dressed speakers today. I wore my best hoodie. You can all see. So we're gonna have 3 talks today, right? And our first speaker today, Andrew, is going to tell us about the quantum states of sound. So Andrew, it's all yours.
Okay, so as he mentioned, my name is Andrew Shepard. As you know, this is Northern Arizona University. My advisor is Ryan Bahunin, who is right over here. And today I want to tell you about a powerful application of light matter interactions, and specifically a quantum application. And I'm going to be telling you about quantum states of sound. Okay.
Did you break it already?
Yeah, I must have. This doesn't work either.
Good.
Click on the screen. Whoa. You know everything else. Okay, so I want to motivate this idea, quantum states of sound, before we begin. So why would you ever want to synthesize quantum states of sound? Well, it starts with quantum computing. Quantum computing is at the forefront of a lot of physics discovery, and for good reason. It has the ability to solve highly complex problems exponentially faster than classical computers. So a lot of complex algorithms may take a classical computer too long for it to be practically solvable, whereas quantum computing may be able to solve that. Some of those problems might be like writing algorithms for climate change or new material development. These are all things that we could see benefit from quantum computing. There is one problem with it. It's currently limited by relatively short quantum coherence time. So when I say coherence, I'm talking about how long your quantum state hangs around before it deteriorates back into a classical state. That usually comes from interactions with your environment. One of the leading device components in the field of quantum information science is the superconducting qubit. And that's what you see over here on the right. The superconducting qubit has a coherence time that's around the order of 100 microseconds. So this is kind of what leads us to our proposed solution. We want to utilize phonons in a quantum state to extend this quantum coherence time. When I'm talking about phonons, that's in relation to sound. So we're not talking about audible sound that you can hear. That would be cool if that was quantum, but we're really talking about the vibrations in a material. And vibrations in a material we call phonons in the quasi-particle sense. If you think about light, we have light waves, and then we have photons. We have sound waves, and then we have phonons. So just think about that moving forward. We're really going to be talking about phonons. And why are we interested in phonons? Well, they have a wide array of useful properties that we can utilize for a lot of these quantum applications. First one of those properties that I want to talk about is the ability to be cooled to the ground state. So when you put these things in a cryogenic temperature, you get them near 0 Kelvin, you can get them to their ground state, which allows for easier theoretical applicability. Then the second thing is going to be high fidelity state transfer. So I can do it here. Okay. So this enables swapping between your mechanical and optical domains. Normally in a quantum system or quantum network, you have your quantum information traveling through optical fibers. So usually by that I mean you're propagating light somewhere that is encoding this information, but then you might be storing it in the mechanical domain. So now you're thinking about maybe some crystal that's oscillating. So you really need to be able to transfer between those 2 forms of communication very easily and with high fidelity. High fidelity means that you're not going to lose much of that information upon that transfer. And with phonons and what I'm going to propose, this will be easily done. The other, and arguably the most important property, is long phonon lifetimes near 0 Kelvin. So phonons have this really long lifetime near 0 Kelvin, and there is a gentleman from down here, you can see it from this paper, did some measurements that can lead you to believe that this long phonon lifetime will lead to potentially really long phonon quantum coherence on the order of a few seconds. So if you remember, the superconducting qubit was on the order of 100 microseconds. We're talking like roughly 10,000 times longer coherence time. So that would enable a lot more in the field of quantum information science. So getting into the overarching plan and tying it back into light matter interactions, we want to utilize these interactions to create highly entangled quantum states. And then once we have that, we can then isolate our phonon state and then get this quantum state of sound as I've introduced it. So I want to bring this back to light and matter interactions because this is also a material science program. So I want to talk about light scattering. It comes in two forms, elastic and inelastic. Here in this figure over here on the right, you see elastic light scattering. It's not super interesting. Your kinetic energy is conserved. So when I say that, basically think that your color isn't changing upon the interaction. That also means that your frequency isn't changing. Those are synonymous. So in this example, you have blue light that's going to come in. It's going to reflect off of the air molecules, or not reflect, but scatter. So it's going to change direction, but it's not going to really change its frequency. It stays blue. Now, this is a little bit different when you talk about inelastic light scattering. So here, your kinetic energy is not conserved. So you're going to see a color change, also meaning a frequency shift upon that interaction. This comes in two forms, Raman and Brewer scattering. So what you see here is Raman scattering. This is going to be when your light scatters off of an optical phonon. Over here, this is an optical phonon. You can think of it as these rapid oscillations that are back and forth. This green and orange ball could be a molecule, could be like a unit cell in a crystal. Basically, what's going on is you have this laser that's shining into this unit cell or molecule, and it's causing it to oscillate. This laser has a frequency. We can denote that with omega p. So P stands for pump. Usually in optics, whatever the laser that we're inputting is, we call that a pump laser. And that's going to induce these oscillations. Now we can declare those oscillations with a frequency. We'll call that capital omega. So now they're oscillating at capital omega. And then you'll see that now your exiting light will be shifted, either downshifted by that capital omega, so those frequencies, or it'll be upshifted. And if it's downshifted, you call that your Stokes, or like a redshift. If it's upshifted, that's your anti-Stokes. That's basically what's going on with Raman scattering. But today, main focus is going to be on Brewer scattering, which is going to really happen almost exactly the same, only now we're talking about acoustic phonons. So instead of an optical phonon, that's like a rapid oscillation, we're talking about acoustic waves that are propagating throughout your entire material. So let's take a look at what that's like. So this is Brewer scattering. You kind of see it here. Its most basic form, you're going to see, it's called spontaneous Brewer scattering. So think about your pump laser is this blue arrow. You're shining it into whatever your material is, and then it's going to, just like last time, induce these phonons. Now they're these waves that are propagating through your entire material. You can see that as the green line, and then also these ripples. And then it's going to interact with those acoustic waves, so those phonons, and then as it interacts, it's going to shift the light, and then you're going to get a shifted frequency that scatters out. Now you can actually take this process one step further in what's called stimulated Brewer scattering. So now you're stimulating this process with two lasers. So in this case, you're counter-propagating a second laser that's already been shifted at that phonon frequency. So you have two lasers going in, and you'll actually see that that'll drive phonon amplification, and it also amplifies your second laser. So you get a lot of interesting physics that comes from this. And this is inevitably what we'll be using to synthesize these quantum states of sound. I want to talk more about Brewer scattering, so I want to illuminate how this comes about. It requires two things, really, coupling and phase matching. So I want to talk about those. So coupling comes from electrostriction. Electrostriction is when your material is going to compress in the presence of an electric field. That's what you see here. So you have just this crystal that has its pristine shape, and then you apply a voltage across it, and you'll see that it is now compressed. This also happens when shining your laser into your material. So we have this laser, and we're shining it into our material, and then that electric field from the process of electrostriction is going to then induce these compressions throughout your material, and that's going to induce your phonons. So you can see here that your acoustics are dependent on your pump laser. But then, as I said, your pump is scattering off of those acoustics, right? So whatever your scattered light is going to be dependent on your pump and your acoustics, but then your acoustics is amplified by your scattered light now that you're stimulating the process. So you end up with this dependence on all your modes, your two lasers and your acoustics, and this is what we call coupling. And this is very integral to this process. The next thing is phase matching, and this is essentially the basic laws of physics, conservation of energy and momentum. I like to think about it as whatever you put in, that's what you're gonna get out. So if you look at this figure over here, once again, you have your pump light that's going in blue, it has a certain frequency. So we're talking about frequencies and then also wave vectors, that's the conservation of energy and momentum. So the two frequencies of our Stokes and our phonon are going to add up to equal whatever our input frequency is. So that's going to give us resonance in the system. So you can see you have your Stokes frequency and then your phonon frequency. And your omega p is now equal to the frequencies of your Stokes shifted light and then also your phonon. So that's what you can see here with this equation. Omega p is going to be equal to the sum of the other two modes. This also follows for the wave vectors as well, but this has directionality involved. So you can see that this wave vector for your phonon is like pretty large because they're counter propagating. So you just have to understand, also goes into conservation of energy and momentum. There's some directionality there. Okay, how are we going to take this idea of light scattering and stimulated Brewer scattering to synthesizing quantum states of sound? Well, we have this overarching goal of placing these phonons into a highly non-classical state, and I want to break this down into 3 theoretical steps. So the first one, I'm going to show you how we're going to utilize stimulated Brewer scattering to classically prepare highly entangled quantum states. Then next, we're going to take that quantum state and evolve it through time. And then we want to, third, measure the optical fields of our time evolved wave function, which will then isolate our phonon and just give us a singular phonon quantum state, which will be our quantum state of sound. So let's get into step 1. Basically, the first step of any like quantum problem that you're doing, you want to determine your Hamiltonian. So for those who don't know, your Hamiltonian is just, it simply put, is describing the energy of your system. This Hamiltonian is broken up into 2 parts for stimulated Brewer scattering, H naught and H interaction. Your H naught is going to be a sum of 3 different quantum harmonic oscillators. Basically, you have a quantum harmonic oscillator for your pump, your Stokes, and then your phonon. These like A daggers and the B dagger, those are creation and annihilation operators. So that means like this AP dagger means you would be creating a photon and then a pump photon, and then the AP without a dagger means you're now annihilating one, in case you've never seen that before. And then we also have this interaction Hamiltonian, which is describing the interaction between our 3 modes. So then we get to the second part of step 1. We need to determine our classically prepared initial state. So if you look at this figure that I have over here on the right, this graph, we have the linear entropy that's plotted over the coupling rate times time. So this GT, just think of that as an experimentally controllable parameter. And then the linear entropy is a quantification of your entanglement. All you need to know is that when you're around 1, you have a fully entangled state. So you have a pure state, which is ideal for what we're doing. And then if you're at 0, you have a mixed state. Not really what we're looking for, but you can see that all of these lines can reach some level of entanglement. Well, what are these lines? What are they describing? They're describing some initial states that we can make in the lab. I'm specifically interested in this green one because the blue and the orange are going to be utilizing a single photon, which is pretty hard to make in the lab. Well, the green we can do very easily. So it's just a result of 2 coherent states for our 2 lasers, which is just the standard result of a laser. So this is easy to do. Also, all of these states have a 0 in the phonon state, which is going to be this last one. And that is because we cooled it down to cryogenic temperatures. I was talking about that at the beginning as being one of the advantages of using phonons. So that's our initial state that we're using. So it seems like number 1's been satisfied, but can we let this state evolve through time? So this is where the time evolution operator comes in. So this is this function down here. It's this exponential function. Mainly what you need to take away from this is we can take that first part of our step 1, our Hamiltonian, we can just dump it right down into this function, and then we apply it on our initial state. We determined this was our initial state over here. So we can get our time evolved quantum state by just applying the time evolution operator to our initial state. And then let's see what the result is. Okay, here it is. So we have this time evolved state. It's got all these coefficients and some summation. So it's a lot of crazy stuff going on here, but we have this entangled state that's evolved through time. This first one before the comma is your pump. The second one is your Stokes. And then the last one is your phonon. We don't need to get too deep into what all of this means, but those are the things I want you to take away from it. So step 2 has been satisfied. Now we need to measure the optical fields of that wave function and then try to isolate the phonon quantum state. So here's where you're collapsing this wave function. And this is what you see here. We call this homodyne detection if you're doing it in the lab. But basically, I just know how to do it from quantum classes because I'm a theorist. But this gives you your isolated quantum state if you measure these optical fields and collapse it. So once again, let's see what our result is after we collapse it. Here it is. It's really gross. So we've done the projective measurements, and now we've projected our phonon into its isolated state. And it is a large sum of all of these coefficients down here. Once again, super messy. We're not really going to be able to like tell what that means just by inspection. But we know that we've measured the optical field, so step 3 has been satisfied. But how do we know this overarching goal has been satisfied? We don't yet. So this is where the analysis comes in. So that photon state was really messy, but we can look at it in what's called the Wigner function. And that is this plot that you see over here on the right. The Wigner function is a quasi-probability distribution function that we use in quantum mechanics. So it's very similar to your classical probability distribution functions. However, those cannot be negative, and the Wigner function can. And the negativity is actually showing you where you're seeing non-classical features of your state. So you can see that it drops negative right in the middle of this like volcano here. And then you also have that ring around. So there are negative features of this Wigner function telling us that it's highly non-classical. This is also approximately the n=3 Fock state. So we know what that looks like from just other analysis. The Fock state is a number state. If you're thinking about light and photons, number 3, n=3 Fock state would be like 3 photons propagating around. If you know anything about quantum, whenever you're working with quantized, really small numbers of things like photons, you're in a highly non-classical state. So the fact that this is approximately looking like what we have here with the n=3 Fock state is encouraging for our analysis. Okay, so we've solved kind of all of our goals and our overarching goal. Now, where do we want to take this? Well, this kind of leads me into my current research, which is looking at now forward stimulated Brewer scattering and the quantum dynamics of that, rather than what was previously backwards in the rest of this talk. So what's forward stimulated Brewer scattering? Very shortly, it's when your phonons are now coupling to co-propagating lasers instead of counter-propagating. So if you remember that figure from earlier, that red laser was counter-propagating into that material and causing the waves. Now they're actually going the same direction. It's going to result in a much smaller phonon frequency and phonon wave vector, but it also leads to this really cool cascading effect. So you can actually have now these multiple like Stokes and anti-Stokes shifts that are going to be evenly spaced for the most part from your phonon frequency. So forward stimulated Brewer scattering, you're now getting this almost like a frequency comb of like possible modes. Experimentally, what would this look like? Well, you're sending your pump light into an optical fiber. You're going to let it go around a resonator, which is where the process is really taking place. As it goes around, it's then going to induce a shifted light, and then that light will also induce some shifted light, another mode, and then so on and so forth. And then all of that light will then exit your optical fiber, and now you'll have sort of this quasi-frequency comb. So I just want to go over one kind of simple generated state that we can look at in quantum mechanics. So let's think about taking one photon and just putting it into a general state. So for this case, let's say we're looking at a green photon. So what's going to happen with the quantum dynamics of this after we apply the time evolution operator? Everything's going to, the theory is exactly the same as everything that I've told you so far, but now we're going to get this result out. What you need to take away from this is we have a superposition of chances that it's in any of these modes. And honestly, this n goes for a long time, like to infinity. So think about that we could detect a photon later in any of these modes, and then that would give us direct information about our phonon, because this n here, this negative n, is also the same n that is in your phonon state. So I have a figure to kind of show and demonstrate what this would look like. Okay, we've put a photon in, it's in that 0 state, so it's in this green one. These are all photodetectors here, so they're just looking for a photon. And boom, we measure it, it's in this -3. And then we know that because of the spacing, because of that equal spacing of all of our modes, that our phonon is actually in the 3rd Fock state with obviously some coefficients out in front. But that's just one of the interesting sort of applications of the current work that I'm doing, which brings me to future work and also a conclusion. So future work involves kind of extending the things that I've already been doing, looking at more systems that you can stimulate through light matter interactions. Next, we want to apply this to a lot of current quantum information science research, such as like implementing quantum logic and also creating more exotic states that may be beneficial for quantum information science, such as Schrodinger cat states. And then eventually we would like to obviously study the decoherence of these phonons, because that is how I motivated this topic as the potential solution. So hopefully we could figure out some solutions to some long-standing barriers in quantum information science. And thank you, that's all I
Hey, time for a couple questions, Cameron.
So you talked about how by using this individual time, you can get longer coherence times at cryogenic temperatures. Can you do this at higher temperatures or like how does that?
Yeah, great question. So, not necessarily because at higher temperatures, the phonon lifetime isn't nearly as long as what you can get at those very low temperatures. So there's a direct correlation kind of about what's going on at those low temperatures to the coherence time, and that's just not necessarily the case at higher temperatures because the lifetime just isn't there.
Can you go back to your frequency code? So predominantly you're getting your incoming frequency, yeah, that'll be fine. What's the drop off in intensity as you go away from your major peaks?
Yeah,
Because they're going to get harder to measure the further you go out.
right. I don't know exactly when those drop-offs will start happening, but your index of refraction will eventually start to change, like as a function of frequency. So you'll see that these aren't going to be as evenly spaced. So then this frequency cone will kind of deteriorate because
Not
of
the
that.
spacing, what about the intensity?
Right. Well, I'm thinking when it's not on resonance, that's going to hurt the intensity. So when you're dealing with this on resonance, you're going to see that you have this maximum amount of intensity, but then as now the spacing isn't right, then the resonance of your system isn't correct. So then you'll see that it's not like the perfect process that it was previously. Doesn't buy it.
Any other questions? All right, well, let's thank Andrew. We'll shift here, get ready for. You shut it out, did you? Okay, there we go.
No.
Set up. All righty, so our next speaker today is Ysaris, and well, I'll let him tell you about what he's doing, what he's going to be doing.
All right, hello everyone. Thank you for coming today. Today I have the privilege of sharing with you the product that I've been working on for the past few months called the dynamic photonic communication in supramolecular polymer composites. And this is not working. Oh, we gotta click on the slide first. All right,
Probably
so
need to just eject him.
all right, so let's start off this talk by very briefly talking about nature. Nature has been very incredible in its ability to maintain and support life for many years across various environments. And there are various ways that nature is able to support this life. And one of the main ways that it's able to do this is by having cellular organization or compartmentalization in order to regulate and control complex biological processes like cellular communication. So let's take a very quick look into an example of what this looks like in a photosynthetic context. So here we have a photosynthetic chromatophore. And the interesting thing about this is that you see various circles on here. The green ones on the outside are light harvesting 2 complexes, peripheral complexes. And in the center here, we have a light harvesting 1 complex. And in the middle, we have a reaction center. So the basic mechanism of what's happening here is that one of these peripheral complexes absorbs some energy from the sun. It eventually gets transferred to this final point here, the reaction center, where at this point, some secondary reactions happen to cause that energy to be converted into usable chemical energy for plants. And we know that this process is very, very efficient. The reason that we know that it's efficient is because of some fluorescence spectroscopy data that we have here. So in this data, there are 2 main things that you can take away. First is a high intensity of absorption and emission spectrum, which means that these light harvesting complexes are able to absorb plenty of energy and also able to emit plenty of energy to other complexes for energy transfer. And secondly, we have this overlap of these 2 spectrum, the emission of the donor and the excitation of the acceptor. And without this overlap here, there would simply be no energy transfer that's happening in this system. So this is cool and all, but the next step in this is that, believe it or not, we can also use bio-inspired systems and biomimicry to try to accomplish this similar type of cellular organization. So one example of this that we can use is in a peptide-based system. So the way this basically works is that we conjugate some donors and acceptors on the edges of these peptides. They undergo through some self-assembly processes, and in the end, we get this nice beta sheet looking structure. The main thing to take away from this is that once we get this final state, it organizes our chromophores in such a way where the orientation of them is fixed, and also they're very close to each other. And the important thing to have this energy transfer mechanism work is that they have to be within 10 nanometers of each other, and we're able to do so with this peptide-based system. And once again, looking at similar fluorescence spectroscopy measurements, we're able to see that the same parameters that we want, similar to over here, apply. So we're able to have similar levels of highly efficient energy transfer. So you might now be thinking, why do we want to use bio-inspired systems for this process? Well, there are many reasons. I'm going to highlight two of them here. First of all, we can study complex biological processes in a manner that's a bit simpler and perhaps easier than it will be in a natural system. In this case, looking at energy transfer, for example. And secondly, we can study emergent properties potentially by using this bio-inspired biohybrid materials design. So in my group, we also do this type of work. And we've also used biomimicry to try to study these processes like energy transfer. So here is an example of what one of those systems that we've created looks like. The basic thing that's going on here is we have this membrane. Instead of using a lipid-based membrane, which is very common in a lot of these natural systems, we're using amphiphilic block copolymers. All that those are polymers that have two sides. One side likes water, one does not. And because of this and other favorable qualities, we're able to use them and self-assemble them into these membrane-like structures. And on the inside, we're able to encapsulate various concentrations of light harvesting chromophores. In this case, since we're looking to replicate a natural chlorosome found in green sulfur bacteria, we can have different concentrations of bacterial chlorophyll F, E, D, and C, which are found in these natural chlorosomes. And we can replicate similar concentrations of the natural version, or we can look to have different alterations and combinations of these to see if we can get energy transfer that's potentially even more efficient than what we see in these natural systems. So this is just a very brief introduction to why we want to use bio-inspired systems to study these complex biological processes. However, there is a limitation. These bio-inspired photonic assemblies typically do not behave like natural systems. You might be wondering, what do you mean by that? Well, let's get into it in this next slide. So in these natural systems, there are two types of communications that we can see. The first of these is intercomplex communication. So if I take this blue diamond that I have here and I define it as a single complex, let's say one of the light harvesting two complexes that would initially absorb the light from the sun. And I want to have communication that is limited to this complex. That is what intercomplex communication is. If we want to now compare that to intercomplex communication, that is going to be defined as communication that happens between complexes. So if I want to communicate, let's say from here to here, that is going to require intercomplex communication that transcends a single complex and is able to communicate with various complexes. So if we take a quick step back now and go back to the natural system that we were looking at previously, what kind of communication does this exhibit? Well, this exhibits both, because we can see that in order for the energy to get from this peripheral complex here to the reaction center, there must be some intercomplex communication and these paths that it takes. And additionally, in order for this intercomplex communication to happen, we must have energy transfer that happens in here, and here, and here. So very clearly, we should be able to see that nature uses both types of communication. So once again, if we want to compare these to the bio-inspired systems that we were looking at previously, what does this look like? Well, if we take a very quick look, this looks more like this than it does look like this. And the reason for that is because these two systems here and other systems that we tend to see that are bio-inspired tend to have cellular communication, or in this case, energy transfer that is limited to only the systems in place here, and that doesn't transcend and communicate with other complexes. So for the most part, most of these bio-inspired systems really are limited to this intra-complex communication. So at this point, we're going to start getting into what our main research question is. What are we trying to answer? What is our question? Well, our question is, can we create a bio-inspired system that facilitates the study of intercomplex communication and expands on this higher level organization that we see in these natural systems? So at this point, we're going to get into what my project is. I'm going to talk about three aims that I have for this project and briefly describe what each of them is. The first aim that we have here is we want to create robust monodisperse polymer microbeads using microfluidic strategies. I'm going to go over what these polymer microbeads will be and what microfluidics is later on. For now, I'm simply going to describe the polymer microbeads with this green sphere that I have here. Secondly, what we want to do is organize these amphiphilic block copolymer nanocomposites, similar to the one that I showed you earlier on that we've done in our group, in polymer microbeads. And we want to demonstrate that inter-nanocomposite communication that we talked about earlier. A way that this is going to look, a representation of this, is we're going to have these nanocomposites, some of them with donors, which are going to be receiving the energy from an exterior place. And we're going to have some with acceptors, which are going to be receiving it from the donor. And we're going to try to see if we can measure some force of resonance energy transfer from that by using similar fluorescence spectroscopy techniques that we talked about earlier on. And finally, we want to see if we can control this energy transfer or communication by environmental factors, similar to the way that nature does. So in this case, for example, if we change an environmental factor, like for example, the pH, we can increase the length of the membranes by which these nanocomposites are stored. And by increasing the length of this membrane, we get past that 10 nanometer threshold that we need for energy transfer to happen, and we can essentially turn on and off this communication that we're looking for. So this is basically what the project that we're looking at describes. And for the purposes of this talk, I will only be focusing on this first part. So let's get into it. So we're going to be using alginates for these polymer microbeads. What is alginate? Why are we using alginate in particular? Well, it is a naturally occurring biopolymer that is found in brown algae. It has many favorable qualities, some of which are biocompatibility, low cost, high availability, and non-toxicity. It can additionally also be used to encapsulate biomaterials such as cell cultures, medical drugs, and other types of synthetic scaffolds. And you can imagine, because of the ability to encapsulate these things, it has very, very good applications in the medical field with things like drug delivery, wound healing, etc. So this is what this actually looks like. Here you can see we have various monodispersed alginate microbeads on the order of a couple hundred microns. And as you can see on the right here, with various imaging techniques, we're able to see that once we encapsulate these cells, we're able to distinguish from viable cells and dead cells. The main takeaway, once again, is that we can use this to encapsulate other biomaterials. And I'm going to expand on this a little bit later on, but because we can encapsulate, some biomaterials, this tells us that we're able to encapsulate our nanocomposites and try to see if we can have that intercomplex communication. So the next question you might be wondering is, how can we actually go ahead and create these alginate microbeads? In a bit of a brute force manner, we can do it like so. We can synthesize some alginate pre-gel solution, which is in a liquid state, place it in a syringe, and we can drop it into a beaker containing a cross-linking solution. This cross-linking solution is responsible for the gelation process and forming it into these alginate beads. And so I actually went ahead and did this process myself, and I got something that looked like this. So as you can see, we have different sizes, bigger, smaller, and we can get some clumping as well. Obviously, this looks nothing like what I showed you earlier on. And the reason we don't want to do this for what we're trying to do is for two reasons. One, we don't have control over the size as much. And two, we're not really able to encapsulate any cells or the photonic nanocomposites that we want to encapsulate. So very clearly, we need more formulation control over this process. So one of the previous attempts at trying to gain this control at forming these alginate microbeads involves a centrifugal-based method. The basic mechanism of how this works is in this purple. In here, this is called our inner compartment. We have our gelation agent and our cargo. In our case, the gelation agent is the alginate that we're looking to use, and the cargo can be the cells or the photonic nanocomposites that I'm going to be looking to encapsulate. What happens is that we place this device into a centrifuge, undergo some centrifugal force, and out come these droplets once again, and they drop into the cross-linking solution in the outer compartment, and that causes it to go through that gelation process that we're looking for. Now, with this process, we have a lot of control, or we have some control, I should say, over what the size of it is based on how quickly we're having that centrifugal force. And once again, some of our previous collaborators were able to form these type of alginate microbeads and encapsulate various cells going from 100 to 400 and on the order of a couple hundred microns. And this looks great. However, when we recently tried to implement strategies similar to what they used, we got something that looked like this, which are not quite what we're looking for. They're a little bit more amorphous than these. And essentially, we don't really know why we got this instead of this that we were looking for. So it's very clear that we still need a little bit more formulation control over the process that we're trying to do. So I want to take a quick step back and remind everyone of what my goal is. My goal is not to create a treasure chest that's going to store items. That's not what we're trying to do. We've already seen that we can use these alginate microbeads to store things like cells and other things, but that's not what I'm trying to do. What I'm trying to do is, because we can use alginate to store biomaterials, we want to see if we can store the photonic nanocomposites that we've already shown we can make to have higher order structure, higher order level of organization. And with this higher structure, we can try to see if we can understand things like energy transfer in a manner similar to natural systems rather than things that are limited to intra-complex communication. So I want everyone to remember that this is what we're trying to do. We're not simply trying to use this to store things. So if we go back to what our main research question is at this point, it is how can we obtain more formulation control over what we're trying to do? So if you remember earlier, I said that we would be using microfluidics techniques for this. Why do we want to use microfluidics? Well, this gives us that control that we're looking for in the form of a control of the surface area to volume ratio, which means the size. This gives us additionally that identical fabrication and amount of dispersity that we're looking to have in the system. And we can finely tune the droplets in both the size and the composition. The basic principle of how these microfluidic strategies work is that we disperse a phase into another continuous immiscible phase. And I want you guys to remember this word immiscible because it's going to come out later on. Let's take a look at how microfluidics works. So here we have that example of dispersing a phase into another continuous immiscible phase. In the middle here, we have these green parts, which are going to be our dispersed phase. And then once we get into this clear transparent part, that's going to be our continuous phase. What's happening is that once this comes into contact with this middle phase, some forces get exerted and some processes happen where they eventually get formed into these beads. There are various types of junctions that we can use for this. These are 3 commonly used types of junctions, but I'm going to be using the co-flow junction, and we're going to talk about why we're going to be using that junction later on. And there are various applications that we can have with this. We can have solidification. We can generate Janus droplets, as we learned from Eva last week. And we can also generate some double droplets. For what I'm trying to do, I'm going to be looking to have some solidification happening because once again, once these get sheared into these droplets, we want to see if that cross-linking solution can cause our alginate liquid phase to turn into that gel-like phase. So just expanding once again, we want to have more control over various parameters, such as the physics and the chemistry of the system, which we're going to talk about a bit later on. We want to have a consistent reproducible methodology with this, and this hopefully gives us that so that we can, once again, create complex systems for the study of intercomplex communication, similar to what I told you all in the previous slide. So let's take a closer look at what's actually happening in this co-flow geometry-based microfluidics. So there are 2 things that we want to do. The first of these is, once again, shearing that dispersed phase into spherical droplets with the continuous phase. That's the first step of what we're trying to do with this. So if we take this figure here of what this co-flow geometry setup looks like, we have our dispersed phase in the middle, which is our alginate solution, and we have our continuous phase on the outside. So once again, this continuous phase is going to be flowing out of this outer nozzle here, which is going to be our glass capillary, and this inner nozzle here is going to have our dispersed phase. So the way that fluid dynamics works is that if you're flowing in a certain direction, let's say in this case from left to right, you're always going to have a decreasing pressure. And as a result, because we're flowing in this direction, this continuous phase is always going to be exerting a shearing force in that direction on these microbeads, on the dispersed phase, excuse me, so that we can hopefully form the microbeads. So there are 2 types of regimes that we can have when we have fluid dynamics and flow in a fluid in systems like pipes or in air. And these are a laminar flow regime and a turbulent flow regime. So laminar flow regime looks something like this, where we have a slow, consistent, steady flow going through a tube. And turbulent flow regime is at higher flow rates, higher velocities of liquid, where we have a bit more chaotic and we have something a bit more chaotic, which is not really ideal for what we're looking for. We want to stay in this laminar flow regime. How can we stay in this laminar flow regime? Well, we have to take account of this Reynolds number parameter. And the basic mechanism of this, or the parameters of this, are that we have this density here, the density of our continuous phase. We have the velocity of this phase, L, which is the linear dimension, or in our case, it would be the cross-sectional area over which this is being exerted. And this denominator term has to do with the viscosity of the phase. Without dabbling too much into changing the cross-linking solution itself and changing concentrations, we have very easily access to changing this velocity by changing the flow rates of the phases. So that's the first thing that we're trying to do. Secondly, what we're trying to do once again is cross-link or gel the spherical droplets and solidify them into those gels. So let's take a quick look at what some of my preliminary results have been. We got something that looks like this. This is what's called jetting, long spaghetti-like strands. You might be asking, why are we getting these results? Well, if you remember earlier on, I had stated that there is a physics side to this and there is a chemistry side to this problem. Let's take a quick look once again at the physics of the system. As I said earlier, because there is a flow that's always going from left to right in the system and a decrease in pressure, there's always going to be an intrinsic shearing force that's being exerted on this that we can change simply by changing the flow rate of our continuous phase. But additionally, in order to have these beads form properly, we need to have a pinching force that is exerted on these beads in a certain manner. If there isn't enough of a pinching force exerted, we're going to get something like this, which is what we got. So how do we get this pinching force? Well, I don't have too much time to go over it here, but essentially we want to have a pressure gradient force. We want to have an understanding of how controlling the different pressures in this vertical region here can cause a pinching force to be exerted on those droplets. And by understanding those fluid dynamics, we should ideally be able to exert a proper amount of pinching force and shearing force to get this result here, which is what we're looking for. Secondly, once again, is the chemistry of the system. And that has to do more with the rates of gelation or polymerization. In this case, there are two ways that we can control that, simply by controlling the phase concentrations of our alginate solution and our cross-linking solution, and also by looking at potentially changing our gelation agents. So we want to have a slower rate of gelation in this process once it reaches this last capillary and it has already been sheared into droplets, because with a slower gelation rate, we can get more mechanically robust and ideal systems. So if you remember earlier on, I was talking about something called immiscibility. Well, what is immiscibility? Immiscibility are if two phases are immiscible, that means that they have a high interfacial tension between them. And if you want to think of an example which can illustrate that, you cannot mix oil and water together because these systems are highly immiscible. They have a very high interfacial tension between them. So that, if you recall, the basic mechanism that I said microfluidics is based on is that you disperse a phase into another continuous immiscible phase. Unfortunately, our systems here lack immiscibility. So sorry. Yeah, our systems lack immiscibility. So because of that, if we cannot leverage the physics and the chemistry of the system, we're going to have to do what these groups might have done, which is use a hydrophobic solvent, such as some type of oil, to increase the immiscibility of our systems. So once again, very briefly, bio-inspired supramolecular assembly can be used to study complex biological processes. And we talked about how we can use these alginate microbeads to demonstrate this dynamic into nanocomposite communication. As part of our future work, once we're able to form these alginate microbeads, we want to synthesize them in alginate microbeads in a setup that looks similar to this, where we're going to have our polymer micelle nanocomposites in the center, encapsulated on two sides by the alginate pre-gel solution, and once again sheared and cross-linked with this cross-linking solution. And we want to see if we can have communication and regulate this communication. So I want to thank my advisors, Dr. Gabriel Montano and Dr. Greg Guillera, Jorge Munoz, who has been working very diligently on this with me. I wouldn't have gotten as far as I did without him. And of course, all of these lovely people that make up our APMS and MENA family. So thank you.
And for quick question. Is there an ideal size for these beads?
Not necessarily. For now, we're looking at just having it be a couple hundred microns, because that's really what a lot of the people out there have done. But eventually, I guess we do want to get smaller, but for now, we're just focusing on being able to produce them. Eventually, we're going to have them try to get smaller.
One more.
So when you're going into the next step and you're going to be putting the cells into the microbeads, will they be like in the, will they be in the microfluidic setup, like flowing in and then droplets are forming around them, like when you go to put stuff in them?
So,
or is there a different way to put stuff in?
yeah, the way that we want to do this is with this setup. So you're going to have essentially picture three streams. You're going to have a stream in the center coming in, and then on two sides, you're going to have the alginate coming in. And then once it gets to the, once it gets to this continuous phase here, that's going to cause it to encapsulate on the inside. So that's kind of how we're looking to do that. And we should hopefully get something else like that.
Okay, what more?
How do you, I guess, talking in the beginning about intra and inter, like, how is this inter in terms of like, studying how the energy transfers from one complex to another.
Yeah, so we can create systems where there's energy transfer only limited to one of these, but because we're gonna have multiple of these, we're trying to see, and the ones with donors and ones with acceptors are gonna be separate complexes. So if we have energy absorbed by one of these donors, one of the ones with donors, and we can have these be close enough so that they can interact, we're hoping to see some type of communication between these two in a manner that's different than the typical systems that we had earlier on, where that's limited to only one of those composites.
All righty, let's make a start. We are down to our last speaker of the semester. All right, we'll get this set up. That doesn't mean we're leaving early. We're gonna pay attention to Jaden. All right, and this is Jaden. He's gonna be telling us about quantum game theory. All yours, Jaden.
All right, hello, I am Jaden, and this talk is on quantum game theory, but an application to quantum information science. So first, let's talk about game theory. When we hear game theory, we might be thinking that we're going to study sports or possibly board games or even video games, where that is true. We can study these things with game theory, but it's more applicable than that. It is the logical decision-making or the study of logical decision-making, specifically using mathematical models to optimize strategies in these game-like scenarios. I believe it's the second button. So some of our current applications are economics, business, political science, computer science, biology, where all we need is a way to cast different situations as players, and those players need to have moves to study them with game theory. One specific example I want to look at right now is this two-player non-cooperative game, where this group here is using game theory to try and optimize cancer treatment, where we have two players. Player one is an oncologist, player two is your cancer cells. Where the goal of player one is to kill all the cancer cells, the goal of player two is to survive and reproduce. Where our player one is a rational decision maker, they can change the treatment that they're doing, the dosages, and adapt their strategy according to how player two adapts to their moves. Where player two is only able to evolve to current situations and they cannot predict the moves made by player one. While this is all cool, I want to bring our attention back to the purpose of this talk, and that is applying game theory to quantum information science. Before I do that, though, I need to introduce the game that we are playing, and that is called the minority game, where each player has two choices, a 0 or a 1, and this is a multiplayer game, so 2 or more players. And people or the players win if they choose the less chosen option. For example, this two-player game, they're thinking to themselves, right, I'm going to win, I'm going to choose this. And then at the same time, they make their choice. In this instance, they both chose 1, meaning they both lose. However, they can choose opposite and they can both win. And this is unique to the two-player game. Another example is a 3-player game where we introduce one more player. Still, they're thinking to themselves, I'm going to win this. They make their choice at the exact same time. And now our blue player wins because they choose 1 and they are in minority of this game. It is important to note, however, that they all can choose the exact same and they can all lose in this game. What I want you all to take away from this is that the minority game is very useful when there are two choices to choose between, and we'll see that later in our application. But now I want to pose this question. What if players had some sort of inside knowledge or a way to communicate with each other? And I would say that is cheating. And we don't like cheating in games, right? That would defeat the purpose of studying these games. However, we can use quantum entanglement to work our way around this no cheating aspect, where the idea with entanglement is we have 2 or more objects, and we can do some mathematical operations to them to entangle them, or to have them correlated in such a manner that no matter how close they are or how far apart they are, you will have some information when you measure one about the other one. And like I said, it's 2 or two or more objects that can be entangled. What's really cool about this though is with game theory and this quantum entanglement, we have quantum game theory, which will increase our probability of success when playing these games. So now I want to talk about the quantum minority game, where now we utilize this entanglement and we have three choices to choose between. So the 0, the 1, and now our Q move or our quantum move Q. And it's important to note that players will win with a higher probability of success when they choose Q. And because we have rational decision makers, they are all choosing Q. So for our two-player game, we get this state. Or if we were to take a measurement of this state, we always have the players winning. Similarly, the three-player game, they choose Q, and we get this state where if we take a measurement, one player will always win every single time we play this game. So with the quantum minority game, we eliminate the options for every player losing. So now I want to apply this game theory and quantum game theory and figure out the differences between them. Before I do that, I want to motivate why this is important. So I am part of CQN, or the Center for Quantum Networks, and one of our largest goals in this center is to build the first quantum internet, where there's going to be many crucial things to develop this internet, such as entanglement generation, routing protocols, capacity issues, error detection and correction, and many, many more. And I believe that game theory and quantum game theory can be used to, or used and applied to many different things on this list. For us, I am focusing on the routing protocols. Here are two example networks that I'm applying these games to. Here we have multiple pathways and then a congestion type scenario inside of networks. How I'm going to be assessing these games is with three criteria: the probability of success for sending one and only one qubit on each network channel, the fairness for all qubits, and then the efficiency of resources used. So our first one, we're going to be looking at our multiple pathway channel, where if the players choose 0, they go on the top channel, 1, they go on the bottom channel. So we have 4 different possibilities of occurring, which look like this, where our top 2 options are good because they are being sent on opposite channels. Our bottom 2 are no good because the qubits are being sent on the same channel. So now, and analyzing this with our 3 criteria, our probability of success is 50%, and that is because our top 2 are good, bottom 2 are no good. Okay. Our fairness is 100% because it's essentially a coin flip that they choose the top channel or the bottom channel, a 0 or the 1. So it's 100% fair. And then our efficiency is 50% also because our bottom 2, they're not using the full network that we want them to. So with a similar analysis, we can go to our congestion network, where now we have 3 qubits playing this game. When they choose a 0, they do not send, a 1, they do send. So we have 8 different possibilities of occurrence, where our top 3 are good. There's only 1 thing being sent on each network channel. Our bottom 5 are no good because 2 or more or 0 are being sent on these channels. So our probability of success is 37.5% or 3/8. And that's because our top 3 are good, bottom 5 are not good. Our fairness is 100% because again, it's like a coin flip choosing 1 or 0. And then our efficiency is also 37.5% because our bottom 5 are not using the networks like we want them to. So now I want to compare the minority game with the quantum minority game with those same network scenarios, where before classically we had these 4 possible outcomes for this. But introducing our quantum, we have this state where it's impossible in this state to use or to send on the same channel. So we can eliminate these bottom 2 outcomes. Now we can assess this scenario once again. where our probability of success is now 100% because in either outcome, they're sending on opposite channels. Our fairness, again, is 100% because in this state, our blue triangle and red circle have equal likelihood of being a 1 or a 0 when measured. And our efficiency is now 100% because in both scenarios, we're using the entire network like we want them to. Again, let's do an assessment of the congestion network where we are using quantum. So we have this state now, and with this state, we eliminate the possibilities of these bottom 5 scenarios even occurring. So we can get rid of those. And now we can assess this once again. Our probability of success is 100% because in each scenario, only 1 qubit is being sent on a channel at a time. Our fairness is now 100% because each qubit has the same likelihood of being a 1 or a 0. And then the efficiency is now 100% because in each outcome, we have the network and it's being used properly. So we all know the classical internet has errors, and so will a quantum internet, and likely it will have even more errors. So what happens if we add in an error? And we can do so using NetSquid, which is a quantum network simulator where you can change all the parameters that you want. For us, I changed this bit flip error, which is going from a 0 to a 1 or 1 to a 0. For example, if we look at our 2-player state here, if we have all of these bits flipped, we would have this state. It is very subtle, but what we see is that this is equal to that. Okay? And that's important with the results. And then for our 3-player state, we start with this. And if we were to flip all of these bits, we would have this, which is not equivalent to that state that we just had. And you'll see why this is also important when we talk about results. So these results correspond to our multiple pathway network, where our x-axis is the probability of that bit flip error occurring, and our y-axis is the probability of success. Where I want to highlight 3 positions on this bar graph, 0, 50, and 100% errors. If we notice our 0% and our 100% errors, they are equivalent. They're both at 100% probability of success. And that is due to this state being equivalent to when you flip all of the bits. Okay? And then I want to bring our attention back to our results, where this line here represents our classical probability. Okay, so at 50%, we reach our classical outcome, which is a good result. And we can conclude from this that even with bit flip errors, our worst outcome is no less than our classical outcome. Now I want to look at the results with our congestion network. And again, I want to highlight these 3 positions on our bar graph. We can see our 100% error rate is 0% probability of success. And that is due to the nature of our state, where these are not equal to each other. And our state with our bit flips, there's multiple ones in each ket, meaning that there's multiple or many qubits are trying to be sent at the same time. Again, let's look back at our results here. This red line again represents our classical probability of success, where at 50%, we have that outcome. So we can conclude that our quantum minority game is better until after 50%. However, with a network, if we have lots of errors in them, we wouldn't want to use that network anyways. So I want to highlight these 2 bars on our graph that are significantly better than our classical outcome. So for future, I'm going to start shifting my focus to entanglement generation. And once I do that and get some results, I'm going to compare those with other groups. And I also want to keep developing my foundational knowledge of quantum game theory and become better and better with that. With summary, quantum games can boost our probabilities of success. We can mitigate congestion, maximize resources used, And even with some errors, like the bit flip error, our outcomes are better than classical. Acknowledgements, thanks to our class for hearing this many times and going through iterations with me. Thank you, Dr. Inez Montano and CQN for funding this research, and my wife for hearing this more than anyone else.
All righty, any questions?
Would it be beneficial to look at any other types of errors besides the flip error?
Yeah, for sure. There's tons of errors that can happen, but this is just for today, yeah.
Excuse me, this for the study session?
No, this is a seminar. It might be happening after. That's all right.
Yeah, probably at 5.
You want to answer that question? Sorry.
Yeah, come back later. Yeah, so how I had it, it was a probability of flipping each bit, but if it's 100% flip, then it would flip the entire state. So that's why at like 50% error rate, it basically becomes classical, it's just a random chance of being 1 or 0 again.
So did you understand all of these? Yeah, then you'll have to go again. That was the, for setting the box. I think.
So for your next steps, times for the containment generation, you kind of have a game plan in your head on like how you're gonna take those next steps. Are you still thinking about it?
Yeah, I am going to try and, I'm looking at Ash Leish's paper and trying to cast that in like a game type scenario. So those are the plans, basically making a list of all the different parameters and people and that sort of thing. Yeah. Yeah. It's an entanglement generation paper. Yeah.
All right, well, with that, let's thank Jaden and all our speakers. Thank you all for being here. And we will see you all next semester. And that'll be our parting.
Yeah.